Hello everyone. So today, as you can see, I'm going to be going over Newman projections, and specifically I'm going to be going over butane. So even though I have this whole thing up, please don't just take a picture and then leave. I'm going to actually go into detail and explain it, because if you just copy it, you're not going to know it, and you're not going to know it on your exam. And so I'm going to walk step by step how to do these projections, and the ways and the tricks and tips and tricks that I use to get an A in organic chemistry, and how I was able to do this Newman projection specifically on my exam, and just how that way, because at first when I was learning Newman projections, it was super difficult for me because I didn't know how to see it. I wasn't very good at imagining it in my head, and so I wanted to give you a practical way of how to do it, because I know a lot of students organic chemistry, at first they have to kind of figure out how to think in that way. So before I actually begin this video, I just wanted to say the full video is going to be on YouTube, and on YouTube I have everything by subject: chemistry, organic chemistry, biochemistry, etc. And hopefully soon I'll be able to add even more subjects. And again, this content really takes time to draw all of these structures and explain it and have things prepared for y'all. It takes time, so please follow, comment, share, and follow me here and on YouTube. And now let's get back to the video. So today we're going to be talking again about Newman projection stuff. And so what I drew was butane. So I drew butane in a different way. As you can see here, this is the actual structure. You have this line, but I wanted to kind of show the hydrogens, because that's what trips people up, is they kind of don't know how to actually see the projection. So I'm going to act like if I'm looking through this way. I'm drawing an arrow, I'm going to look through this way, and this is going to be the carbon that I'm focused on that's in blue. And what you're going to see is, you're going to see this hydrogen is on the left, this hydrogen is on the right, and this one is down. And that's what I have right here, on the left, on the right, and down. So that way you guys can kind of start visualizing it. Okay, then what do I see? I see that this so this is the thing, as a pause. So this is in front, so it's drawn like this, okay? Then what's in the back is just gonna be here, like a little stick. So these are in the back, what's on the circle is in the front. So that's first of all. So think about it like this is the circle, so this is the front, and then these are the little lines that are sticking out in the back. So I'll try to draw a better circle so you guys can kind of see what I'm talking about. So this is in the front and that is in the back. So I put things in color so you guys can actually see it in the diagram. So again, you're going to see this carbon on the top, the CH3. You're going to see this hydrogen on the left, bottom left, on this hydrogen over here on the right. Okay, so you guys don't get lost, and I have all these letters up. I literally have, for example, the hydrogen in blue, I have it in the drawings, so you're going to be able to see it in blue or in light blue, or the CH3. So let's actually begin. So that basic drawing that I told you is here. So this, I transferred it over here of what you see. So that CH3, like I said, you see it on the top. This hydrogen here, you see it here. And this hydrogen light blue, you see it here. It's in the back. And this whole thing is in the front. So we got that. Now what you're going to do is you can choose. Either you keep the front the same and you rotate the back, or you keep the back the same and you rotate the front. I'm going to say that again. You keep one side the same and you only rotate the other side. Don't rotate both sides, because you're going to get a hot mess and that's not going to work. So you need to rotate only one side. In this video, I'm only rotating the front. If you notice, The back is the same. I never changed this. It is the same throughout, and that is what you need to do. So if you like this method, then do that. Keep the back the same and just rotate the front. And the amount that you're rotating is 60 degrees. So imagine that you have this circle and you cut it literally in 6 pieces. Like, that's what you're doing. You're just rotating a little bit, then rotating a little bit, then rotating a little bit, then rotating a little bit, until you do the full 360. That's what you're doing. So right now, I'm going to show you. So this hydrogen is going to come down a little bit and be right next to that hydrogen, which is what happens. But in the same way, this CH3 is going to rotate a little bit and be with that hydrogen. And then this hydrogen right here in red is going to be right next to that CH3 over there. And that's what you have in the next one. Now what you're going to do, you're going to do the same thing. You're not touching the one in the back. You're just doing the one in the front. So now you're going to move this hydrogen over here a little bit in the middle. That's what you did. You moved it to the middle. And now this one, you're like, okay, I need to move it to the middle as well. And so it goes to the middle. And then lastly, this CH3 is like, okay, I need to go to the middle as well. And it goes to the middle as well. So I'm going to erase those arrows so that way it doesn't get too hectic and you guys can see the actual picture. So then you end up with the next frame. Then in the next frame, you're going to put this CH3 over here. And you're going to put this hydrogen over here. And you're going to put this hydrogen over there. And you keep doing this process until you end up with exactly the same. Okay, so then when it makes the full 360, that's why in here I put 360 or 0 degrees, because you make a full chain circle. Now, the reason I began with 180 degrees is because they're an anticonformation, which I know I'm throwing these words at you, but I'm going to explain what anticonformation is. So anticonformation is when you have your two largest groups 180 degrees away from each other. So it is the most stable. If they ever ask you on a test, what is the most stable position? It's anticonformation. Okay, so let's go over these terms. So eclipse, think of a literal eclipse, one thing on top of the other. I literally can't put these two lines because you're going to be confused. So what chemists do is they put the lines next to each other so you know that it's an eclipse conformation. But in actuality, it is stacked on top of each other. Like it's one right in front of the other. Okay? So in chemistry, we draw them right next to each other. Now, staggered conformation is when you have space between. So like here, this is not stacked on that one. They're like they have enough space in between them. Okay? And then you have what is known as gauche. So gauche is when you have your two big groups in staggered but kind of next to each other. So this is gauche. Gauche actually means left in French. So if you think about it, this big group is to the left of this big group. And then here you have gauche again. So this group is to the left of this group, and that's in the darker blue. So it's not that they're on top. It's just that they're next to each other. So that's gauche. And therefore, it requires it's more energy than just a regular staggered conformation. And then eclipsed is going to be the highest energy because it's like a torsional strain and all of that, because you have those groups like in front of each other and they have a lot of strain. So this is the worst. The CH3, well, not just the CH3 stacked on a CH3. In this case, those are the two largest groups, these groups right here. But it can be whatever two are the biggest groups. If they are stacked on one another, that is going to be the highest amount of energy. And therefore, it makes sense why anti-conformation is the lowest, because they have the most space apart from one another. They're like 180 degrees. They're polar opposites. They have the most space possible to be away from each other. So keeping all of this in mind, you have to do energy diagrams. So energy diagram, I tried to make it nice. I don't know if it too many colors. You guys can comment that, but I wanted you guys to see how you go about drawing it and not just see random dots on this page. So first of all, for the energy diagram, you have to label from 0 to 360. And the reason I put 0 at the end is because it goes, it's a circle, right? So it goes over and over and over again, and you end up where you began. So it's spaced by 60, which represents each turn, like not turn like full turn, but like the partial rotation. And then that's why it's called degrees of rotation. And then on the y-axis, you can see energy, and it's going to tell you the amount of energy. In this case, I'm doing kilojoules per mole, as you can see on the bottom. And usually in chemistry, they'll give you like a little chart, and it'll say a hydrogen with another hydrogen eclipsed is going to be 4. A hydrogen with a methyl is 6. 2 methyls are going to be 11. 2 methyls in gauche are going to be 3.8. And the way that you calculate it here at the top, for example, is, okay, lastly, I put the anti-conformation. It is the lowest in energy. It doesn't mean it doesn't require any energy at all, but some people have a little bit of space and other people have it like just at almost 0, because again, it is the lowest amount of energy. And so how to calculate. When you go here, for example, and you see this HCH3 is an eclipse. So that is 6. But this HCH3 over here is also an eclipse. So that now it's 6 plus 6 is 12. And these 2 hydrogens are an eclipse. So it's 4. So it's 6 plus 6 plus 4, or 12 plus 4. So that's 16. So the total amount of energy at 240 degrees is 16, which is why, I have it noted as 16. So that's how you calculate the amount of energy per each. And then when you know how much energy is in each, you're able to kind of draw the energy diagram. So I hope this video helped to really explain how to draw these Newman projections. And notice it can be, if it was an even longer chain, you have to choose which carbon you're seeing through the lens, and that's the hardest part. But if you're not, you can't imagine it in your head, my trick is you choose one carbon and you see the position. So I chose this carbon right here, and I said, okay, this is going to be on the left, this is going to be on the right, this is going to be down. Okay, this is going to be the other carbon that I'm going to choose in the back. This is going to be on the top, this is going to be on the bottom left, and this is going to be on the bottom right. So that is my trick for doing it. If you can't, if you're not like visually seeing it like it was in my case, I had to come up with that. And I hope that this whole video helps you see and understand the differences. And as a recap, eclipsed is the highest amount of energy. Then it's staggered, and well, technically it would be gauche, and then like regular staggered, and then the lowest is going to be anti-conformation. And now, thanks again for watching this video. And again, if you enjoyed it, please follow me here and on YouTube. And thanks again.